Convair Aerospace General Dynamics is developing new techniques in computer-aided design using interactive graphics. I am Ken Bonine, the project leader of the implementation of interactive graphics at Convair. By computer-aided design, we mean the situation where the user converses directly with the computer and his problem-solving process is continuous and uninterrupted. The cathode ray tube, such as we see here, is the tool that provides the direct communication link between the user and the computer. The cathode ray tube displays alphanumeric text and line drawings of the output of the user's program as it is being produced. The user may view this output, may stop the program, may modify input, and restart the program using the light pen. We have here the light pen is sensitive to the picks on the face of the tube, and these cause program branching in the main computer and affect the changes in the program. The advantages of using this type of tool are that you can save time, product development time, the product cost can be reduced, you can improve the quality of the end product, you can stimulate creativity of the user by keeping his problem-solving mode uninterrupted, keeping his mental momentum up, and you can produce a competitive edge in being able to respond more quickly to the marketplace and the user demands on changes in the product. The approach Convair has taken is to build a broad base of users utilizing from different disciplines, developing software that can be used in their ongoing work. We are training about 140 people in this particular process. 25 have been actively engaged in developing programs. The present computer configuration at Convair is that for scientific work we have a Control Data 6400 computer with 65,000 words of central memory at Kearney Mesa facility. We have this terminal at the Kearney Mesa facility and one more graphic terminal at Lindbergh Field, which is 10 miles away. The following examples are the types of programs that we have developed and are using in our work today.
I am Don Peterson, a Senior Design Engineer at the Convair Division. The program I have developed helps mechanical designers synthesize 4-bar linkages for several classes of problems. The program saves design time, primarily in the pre-design phase, and allows the designer to develop optimum solutions. This is a list of options which allows the designer a choice of the type of problem he wishes to solve. Each choice represents a different set of motion constraints. To demonstrate the program, I shall select the first constraint option, 4-position coupler guidance. After defining the constraining positions, loci curves are calculated and displayed. These curves define the set of 4-bar linkages which will exhibit the desired motion. Linkages are selected from the curves by positioning the tracking cross somewhere along the fixed pivot curve and accepting its location with the light pen. The construct option allows drafting to be done about the link center lines obtained from the curves. Points, lines, arcs, and special figures can be drawn quickly and easily. This construction represents a single-slotted airplane flap configuration. Each item constructed is identified with one of the 4 links for animation purposes. The leading edge is drawn using the special figure feature of the construct option. The components of the flap have been specified to move with the coupler length of the 4-bar linkage. The line construct feature of the drafting option is demonstrated by constructing lines which illustrate the leading edge's fixed relationship to the main portion of the flap. Lines are drawn by simply indicating the endpoints with the tracking cross. Points and arcs can be constructed with equal simplicity. To rotate or animate the linkage, the rotation option is used. The increment of rotation in the direction, clockwise or counterclockwise, must be specified for the link of the 4-bar linkage previously designated as the input link. Intuitively, it can be seen that the direction must be clockwise to obtain the desired flap motion. The light pin switch can now be used to trigger the motion. Each time the switch is depressed, the linkage and flap configuration move one increment in the specified direction. The items constructed are seen to maintain their original relative positions, but together move aft, exhibiting Fowler motion. The linkage illustrated is one of several which could have been chosen from the design curves. All selections will exhibit the same motion with only slight variations. It is therefore left to the designer to select, reselect, and test linkages until he finds the optimum linkage.
I am Sandra Yoshihara, a scientific programmer in the Design Analysis Programming Department. The program I'm going to demonstrate is used to monitor different curve fitting programs and process their data. Through this graphics program, we are able to visually evaluate each curve fit and apply different methods as many times as necessary to arrive at an acceptable fit. Data is read in through cards and displayed in a two-dimensional plot on the scope. The data shown here is atmosphere data plotting velocity of sound versus altitude. We are able to partition the data into segments and fit each segment individually. A segment is defined by moving the tracking cross to indicate the left limit and then the right limit of the segment. The second segment is defined as the first segment by moving the tracking cross to the left limit and then the right limit of the segment. The values of the limits are displayed at the bottom of the scope for verification. The data in the first segment will be displayed and fit with a 6-degree polynomial using the least squares polynomial approximation method. The resultant curve is displayed over the data set. The second segment is to be displayed, and I'm selecting the least squares method again to fit the data, this time with the 11th degree polynomial. We currently have a least squares polynomial curve fit method and an interpolation method in the program, but other methods may be added when they are needed. The curve for the second set of data will be displayed on top of the data set. The original data set will now be displayed with both curves overlaid on top of the data. We have the option to change the scaling of the display by blowing up a certain section to examine details, or by reducing the display to get an overall view. By indicating diagonal corners of an area, I'm specifying a section to be blown up. The data and curves will be redisplayed with the new scaling limit. The original limits of the display are restored, and the data set and both curves are displayed. We are able to visually examine each curve and spot trends or breaks in the curve that are not visible through numerical results. I'm selecting the original data set to be displayed and selecting the least squares method again to be used to fit the data, this time with 11th degree polynomial. Now I'm redisplaying the original data set with the curve for each of the two segments and the curve for the entire data set. We are able to compare the curves and decide on the best fit. Through interactive graphics, we are able to quickly and easily apply different curve fitting methods to fit the data set.
I am Sandra Yoshihara, a research design engineer with the Pomona Division. My program is designed to assist in the packaging of printed circuit boards. using interactive graphics. The input needed is the geometry of the board and a coded electronic schematic diagram. This is a pilot model which was written to show the feasibility of automated packaging. The program itself will not package a circuit board, but instead is a tool to be used by a packaging engineer. Presently, the program consists of two parts, manipulation of components and to make the electrical path hookups. The output options will include the automated hole layout patterns, drill tapes, and assembly drawings. In the first section, the operator is given the option to select node values or actual components. By selecting Pick a Node, the computer responds by displaying a numeric font. Through the use of this internal numeric generator, the operator constructs node values. The computer responds by displaying a list of the node names and their respective leads of the node value. Through the selection of node 2, we can see that the components R23, C2, and Z2 were pre-placed near pin 2, which in this case has a node value of 2. By picking the component name R23, the computer responds with a group of new options. These options deal with the manipulation of the components selected. Printed circuit boards are generally constructed in some basic grid system. The size of the grid, in this case 50,000, is input to the numeric generator. The grid size is retained by the computer and is utilized in an algorithm which automatically shifts the components to the nearest grid. The grid can be erased or redisplayed upon command. By selecting the word Display Vectors, the vectors displayed shows where the component picked is electrically common to all other components. At this point, the tracking cross is attached to the component, and with the light pin, the operator has complete control of the placement of the component. The component can also be rotated in any one of the 90-degree orientations. The computer keeps track of the component's locations and its orientation for further processing. Here the operator returns the component to its 0-degree orientation and then places the component in its original position. When in the display vector mode, the operator may switch from component to component to see the overall electrical picture of each component selected, as a cross-reference to decide if the component should be moved. After displaying the vectors, the program takes the average summation of the vectors on each lead of the component. These new vectors indicate the direction in which the component should be moved for optimum placement. Through the use of these options, the operator moves the components into position. Returning to the main program, we are allowed to enter the electrical path hookup routine. The operator again has various function options which allow him to make the desired electrical interconnections. By selecting a component, the computer displays the node values and their respective leads. The operator can pick a node number, which signifies that the operator is now working with that node. All of the component's leads with that node value have a blinking circle. The operator now constructs line segments from circle to circle, making the desired interconnection. The operator has the option of placing the lines on the top conductor pattern, which is solid, or on the bottom conductor pattern, which would be shown as dashed line. The operator can also add feed-through pads for transferring the signal from one side of the board to the other. The lines and pads with the selected node value will continue to blink until the operator has completed making his interconnection. The operator can also delete lines or pads which may be in the way at later times. By selecting the function number of connections, the numeric generator allows the operator to ask for the nodes which have that number of common components. The operator then selects a new node value to work with. Initial estimates indicate a savings of 60 to 75% in man-hours required for packaging and documentation of discrete component printed circuit boards. This program will form the base of true automation of printed circuit boards from designer through manufacturing. Additional savings will be realized through the automatic output of NC drill tape, NC component selection and insertion tape, and NC Art Master generation tape.
My name is Otto Kurima. I'm an aeronautical engineer, and I'm going to demonstrate to you a Digigraphics high-lift system development program. This program is currently being used to select, design, and develop the high-lift system or flap system for the Space Shuttle booster. This program consists of three major parts.
The high-lift system geometry is stored on punched cards or magnetic disks and can be displayed to the operator upon command. We will see the Space Shuttle flap in partially deployed condition. The flap stows on top of the wing as a protective measure against high temperatures during re-entry. I can move the flap with my light pen. Let us move it back to simulate a track-mounted system. Or a system attached to a 4-bar linkage. I can also rotate the flap, but first one must designate with a tracking cross how much rotation is desired. Should we desire to examine some section more closely, we simply blow it up or enlarge it. How about changing flap or wing contours? First, we move the tracking cross to the area where change is required. Then we pick the contour point to be changed. You might notice a blinking point. And command the change to take place. Let us do it again. We move the tracking cross to the point where contour change is desired. Designate the contour point to be moved and command the move. Well, let us do it on a larger scale so we can really see what is going on. Notice that the contour point that is to be moved is blinking. I have just been accomplishing the operations normally performed by wind tunnel model designers and builders. Once we're happy with the model, we will ask the computer to calculate the aerodynamic forces for us. In this case, we're interested in transient aerodynamic loads during flap deployment. That is, when the flap is mounted on a bar linkage. When the calculations are completed, the aerodynamic lift, drag, and moment data is plotted on the lower right-hand corner of the scope. Let us examine the pressure distributions for an angle of attack. Now let us take a closer look at the pressure distributions on the wing surface. Now we can formulate the next geometric change to the high-lift system. We can display, translate, rotate, or change contours and obtain a new set of aerodynamic data. We repeat the process until we obtain the required data or the desired level of lift. Using Digigraphics, we have been able to accomplish tasks in 20 minutes that under normal circumstances would take 4 to 5 months and involve expensive wind tunnel models and tests.
I am Gary Owing, a scientific programmer in the Design Analysis Programming Department at Convair, and the program which I have written contains the two basic graphical methods needed in designing and testing a control system. Both methods not only predict the performance of the system, but also give insight into how to adjust that system to meet the desired characteristics. The first technique, frequency response, produces two graphs which give the magnitude and phase angle of the response at specific values of frequency. After reading the data, the program computes the points on these curves and displays them. You will notice that the independent variable, frequency, is plotted logarithmically, while the phase angle and gain are linear. By moving the tracking cross to the position we desire, we can determine the exact values of gain and phase at that frequency. These values are displayed near the bottom of the screen. This program also lets me see the effect of a change in the input data. Here I am adding two more poles to the transfer function by entering a new quadratic polynomial in the denominator. The program then recomputes the points on the curves using this new transfer function and displays the plots. To get a clearer picture of the perturbation caused by these new poles, the program displays both sets of curves. This option lets me investigate many similar types of systems and gives me much information on the behavior and volatility of this system. As you can imagine, seeing immediately the results of a newly designed system greatly expedites the search for the best system. I have now decided to utilize the other graphical method, root locus, in order to completely understand the response of this system. This method uses the same transfer function, but produces the plot of the roots of the characteristic equation of the closed-loop system as a function of the gain. After entering values which will define the boundaries of my root locus plot, I direct the program to compute the locus and display the plot. With this plot, we get a clear indication of the effect of gain adjustment on the stability of the system. To get quantitative information from this locus, I choose any point on the plot, and the program returns to me the exact position of that point and the gain and damping ratio there. With this locus before me, I am interested in what would happen if I added a pair of complex poles to the transfer function. Using the tracking cross, I locate the poles at the desired places and direct the program to compute the new locus. Note that the new system is no longer completely stable since the locus now crosses the imaginary axis, the vertical dotted line. By using the comparison option, I can get a more dramatic representation of the effect that these two new poles have had on the original system. If this new system is not satisfactory, I merely have to repeat the above steps using the knowledge I have just gained to design a better system. To summarize, these two graphical methods, frequency response and root locus, provide the tools necessary to completely study the response and stability of any control system. More importantly, this program and its use of interactive computer graphics has provided the medium through which the engineer can use his understanding of the problem to efficiently direct the processes needed to design and test a control system.
I am Michael Kronk, a structural engineer at Convair, and I have written a graphics program to develop three-dimensional structural analysis mathematical models. The first part of the program is used to visually check out the structural model and to make changes and corrections to the model before it is analyzed.
In the first part of the program, we develop an overall view of the model by selecting bars to be displayed. We then select a general transformation to define the orientation of the view. The three angles are projections of the model axes onto the tube face. Exploded view factors are set to 1. Picking plot produces the view of the wing. From the overall view of the wing, we can locate errors in geometry and omitted members and decide which areas of the model we wish to study in detail. We now go to a display of a rib of the wing for detailed viewing and modification. As the first check, we display the shear webs of the rib. After checking the webs, they can be erased. The rib will now be shown with a diagonal member that has been added from the tube. As an illustration of changing the geometry, we interrogate a node to determine its coordinates. New coordinates can then be entered from the tube. In this case, the z-coordinate is changed from 13.4 to 15.0 inches. Picking redisplay gives the rib drawn to the new geometry. After the model is analyzed, an overall view of the model in the deflected shape can be constructed. Picking bars in the coordinate transformation followed by plot produces the deflected view in dashed lines. The deflections of the wing are shown to scale. A comparison of the deflected and undeflected shape of the model can be shown by redisplaying the static view. Overlays of several loading conditions can be produced in this manner. Returning to a display of the rib, we can look at the bar results to view a plot of the bar loads in the rib. We can also display the loads in an individual bar for up to 8 bars. This yields exact load information for the bars. Now we see a view of the rib with the panels and the average shear flows. Picking the panel gives a view of the individual panel with the shear flows acting along each side. In this fashion, the structural engineer is able to rapidly view the results of the analysis. This program was used to help develop 3 math models during a recent proposal. The estimated savings compared to 3 similar models for a previous proposal without graphics are 20 to 1 in computer costs and 3 months to 3 weeks in calendar time. Graphics allowed us to meet a tight schedule with a high degree of confidence in the validity of the mathematical analysis of these models.